Welcome to Study Loop.
The magnetic field produced by solenoid 1 is confined to the space within its windings and is equal to B1, which is mu naught N1 times I1 over 2 pi r, where N1 is the number of turns in coil 1 and I1 is the current that passes through coil 1. So first, let's find the self-inductance L1 on coil 1, and this is equal by definition to N1 times the flux, the magnetic flux phi B1 multiplied by the current through coil 1 I1. And this is N1 times the cross-sectional area A of the coil over the current I1 multiplied by the magnetic field B1, which is mu naught N1 times I1 over 2 pi r from above. And so now we can simplify this and show that L1 is equal to mu naught N1 squared times A over 2 pi r. And so we have an inductance for only L1. Now we can do the same for L2, and we'll follow the same procedure. L2 is equal to N2 times the flux phi B2 divided by the current I2. And again, that's N2 times the cross-sectional area A over I2 multiplied by the magnetic field B2, which is similar to B1, mu naught N2 times I2 over 2 pi r. And again, we simplify this and we get that L2 is equal to mu naught N2 squared times A all over 2 pi r. And so now we have expressions for L1 and L2. Now, to find the mutual inductance of the solenoid, M, we know is defined as the number of coils in solenoid 2 times the cross-sectional area times the magnetic field strength in coil 1 all over the current flowing through coil 1. And this is equal to mu naught times N1 times N2 times A over 2 pi r. So we can use our expression for the magnetic field from above to get this expression for the inductance. And therefore, if we square this, M squared is equal to all the squared. So that's mu naught N1 times N2 times A over 2 pi r all squared. And if we break this up, we see that this is mu naught N1 squared times A over 2 pi r. So we just separate this, multiplied by mu naught times N2 squared times A over 2 pi r, which we can see from our expressions above for L1 and L2 is simply L1 times L2 as required.